Cool.
It's okay.
Yeah, I actually am going to live stream because there's people going to be in the back who cannot see. So if they have a laptop, they can see what's going on. Yeah. So I just need to know my live stream URL. Let me live stream because there's people going to be in the back who cannot see. So if they have a laptop, they can see what's going on. Yeah. So I just need to know my live stream URL. Let me live stream because there's people going to be in the back who cannot see. So if they have a laptop, they can.
Ik wil Alan Harper too.
What's that?
Ik wil Alan Harper too. Your present.
I don't understand.
Your present will end. Will finish at Harper too.
When we finished,
At Harper too.
oh, 2:30.
Yeah.
We have. Oh yeah, that's fine. It's plenty of time. Plenty of time. You want this one too? I think I don't. I think I don't need it. I don't think I need it. I'm okay.
Do you need this one is?
I don't think. Are we recording it? I don't think I need it. I'm pretty loud. I'm pretty loud. Yeah. Oh. Why? Oh no, I think here. Is it on? Ah, yeah. Okay, better. We start at 45, right?
Yeah.
Okay, 5 minutes. Good. Awesome, thank you. Oh, he's putting another display. This is good.
Yeah.
I see, that's good. Mm-hmm. Yes. Yeah, perfect. Thank you.
Yeah. Cắm được không?
I think we're good.
Đâu đâu em phải cắm để
Oh.
ăn cả hai.
Do you have the? Yeah, I have mini display. You have mini display to HDMI?
lấy
I think it's
máy anh
okay
này.
like this. It's okay.
Yeah, you can use my computer.
No, it's okay. I'll keep my computer. It's fine. Thank you.
Stream.
Yeah, it's a live stream. This is the live stream URL. So I'll
You
tell
have
you.
live stream URL.
This is live stream. This URL right here. That's
Yeah.
a live stream. To
Yeah, yeah,
the
okay.
YouTube URL.
Yeah, yeah.
YouTube, yeah. So you can tell if you want to tell them
Yeah.
it's streaming now if they want to open on their laptop because some of the things may be very small.
Yeah. Continue stream on screen.
It's doing it
It's
right now.
working, right?
Right
Oh,
now,
okay.
yeah.
Yeah.
Yes.
Ở đây streaming cái screen trên YouTube rồi. Đã stream. Bảo mọi người vào YouTube. Vào YouTube cái link này. Hồi đầu sẽ làm ở TV đi. We try to bring the
Okay. I think that's a mirror of this one, right? Same.
but I think we do not have the so we can combine two of them. Because if you have an HDMI, you can put. Okay.
Well, if it's mini display to HD, it's okay, but I don't have.
Yeah. Okay.
Yeah, I don't have any cable.
Okay. Anh ấy phải mang lại. But I think you have the YouTube live stream or something.
Yeah.
Vẫn màn hình điện tử anh dùng được.
You got it?
Cái đấy không dùng được.
Cái màn hình điện tử dùng được.
Không dùng được.
Sao?
Không combine được. Ví dụ kiểu cái máy đây là Pro đúng không? Nếu có HDMI với DisplayPort đúng không? Cắm cả hai vào ấy.
Anh cắm hai được mà.
Nhưng mà đây là không phải Pro.
Đây ở không anh dùng được. Cái màn hình đấy thì anh dùng được. Vẫn là đây. Tí dùng được.
I think time to go.
I think you can start now.
Yeah. Is this on? Can I use this? It's free. Oh, done.
Yeah, sure.
Hello. How's that? That's still pretty high. Okay, good. Hello.
Hi.
Welcome to DevFest. Thanks for coming to my talk. My name's Alan. I realize the room is pretty deep here and the screen is small. So we were trying to get a TV set up halfway back so you can more clearly see the slides. What I've done is I'm actually live streaming on YouTube right now. So if you happen to have a laptop, you can open this link. It will go to YouTube, and my slides from my screen are playing right now. So then you can read it from the back. If you don't have a laptop, you can use your phone. Otherwise, I'm sorry. So I'll leave this up just for a minute so you can grab the URL if you want. Everything is clear?
Yes.
Okay. Okay, hey, we've got somebody streaming here. All right. We've got a viewer. Oh, so you can see my display, but not my, that's interesting. Well, okay, help me debug that. So I'm gonna change the slide. Tell me, can you see me advance the slide? Did you see that? It may take a couple of seconds. It's okay? Am I on slide 2 or still slide 1?
Slide 1.
Still on slide 1.
Yeah.
I think that the ability is not good enough for a lot of people to access Wi-Fi and see your slides.
Well, it may be.
You can
Yeah, it's a secondary display, isn't it?
You can split your laptop into 2 screens and simulate the second screen.
Maybe like this. Here. You are suggesting to do this, right? And then change this to display 1. Okay. Where's my browser? Let's do this. Move this over here. Okay, how about that? I think there's a bit of a delay, but not too bad. Hey, okay, it's kind of cropped weird, but it looks okay. Okay, excellent. So, I'm going to be talking today about some of our serverless infrastructure on Google Cloud. Again, I have an interest slide in a moment, but I'm a developer advocate. I specifically on healthcare and AI applications at Google. By background, my PhD is in human genetics. So I'm specifically focused in medical imaging or genomics or medical records or all things related to health and DNA. Even agriculture is part of what I work on. Yeah. If you want to follow me, I'm on Twitter. I will be posting these slides up online later so you can scrutinize them. Don't feel like you need to write everything down right now. All right, so the whole point of serverless is that a big part of processing data is scaling. Sometimes scaling down is a problem. If, for instance, you're trying to build an IoT hardware device on very limited memory or limited CPU power, limited bandwidth, limited battery, etc. So scaling down to the very small is difficult. Scaling up to the very large is also difficult. And by abstracting away from machines or servers, such as a server in a data center, and representing the problem functionally and interacting with computing systems via APIs, enables some separation of concern, where operations and data center management is on one side, which is what a cloud platform is offering, platform as a service, or these serverless services, services as a service, so that an application developer can focus on specifically the business logic concerns that are relevant to adding business value. All right. So again, just rehashing this is a new deck, by the way, so bear with me. It means that basically, as a user, you're focusing on the deriving insights and adding business value rather than focusing on administration, which is not necessarily part of your core business value. The nice thing is that frequently what you find is that businesses are constantly exploring what types of services might be useful and what is the appropriate scale. And it can be difficult to get that right, especially as business conditions are changing. And so having too large or too small purchases of capital can make it very difficult to the business to become agile and compete effectively. So what cloud is really letting you do is pay only for the services that you're using at the time. When you turn a service, stop requesting services, turn it off, you stop paying. So this creates a bunch of agility for you to experiment, etc. Okay, so all of this really has to do with data processing, and I'm going to talk to you about some different types of data that might be relevant in this kind of context. One particular type of problem that shows up is data that's already being analyzed as part of a business process, but possibly in a suboptimal way. So data that's already being analyzed. For example, one type of data that might be analyzed, this is a picture of the Dragon from SpaceX that's based in Los Angeles, California. If you haven't seen this thing, this is a small cargo payload that is launched on a rocket to ship goods up to the International Space Station. So it goes up approximately 40 kilometers above the Earth to the space station, and then there's some cargo in here that's being delivered. Of course, you can imagine that the rocket and the capsule both have a huge number of sensors on them so that all the data can be collected and logged, some of which is being logged directly on the device, some of which is being streamed live, like we're doing on YouTube right now, over telemetry back to the operations center on the ground. And all of that data will be used to revise both the device as well as the operating systems on the device to improve performance. Okay, so another type of data that you might be interested in collecting or using are data that are currently collected but not well analyzed. So Google, we actually have an example like this, and you can see that this is a picture of a shopping district on the street somewhere. And before we really knew what we wanted to do with this kind of images, we had already started collecting them using the Google Street View cars. So this is a car, there's a human driving it, it's not a self-driving car. It's empty in this case. And there's a camera, this is on top, omnidirectional camera. This is collecting data so that we can get visibility as to what's the surroundings of the vehicle as it's moving down the road. So we started archiving a lot of this data, and as the computer vision algorithms started to improve, and we built CAPTCHA systems for analyzing text, for example, we can start to extract out information from this library of images that were collected, but we didn't know what was in them really. So we can get out things like, street numbers on the street sign, business names, where are the traffic signals, this is particularly important, etc. Traffic signals being important because now that we've analyzed this large archive of historical data, we can start feeding in information from that library into self-driving cars. So in this case, now we're collecting live data, some of it being processed locally on device, additional data being pulled in from the cloud, and additional data being pushed out to the cloud, all from this collection of mobile sensors. Pretty similar to your phone if you think about it. There's a bunch of sensors on here, this thing moves around too. It's just not self-driving, it's a passenger on a human. All right. And so an example of some of this data, let's see if we can play a video in a live stream YouTube. This is from a New York Times article that came out pretty recently. This is actually, if you haven't looked into self-driving car technology, what the car is seeing. So there's some scan lines on here that are related to a LiDAR. It's a invisible laser that's being projected out by the car, and then the reflection of the light is coming back in. We can determine at what distance objects are and roughly what's the shape of them. You can see some things are hidden in the shadow because the shadow is not visible to the camera, right? It's occluded. You can see people walking around and so on. Okay, yeah, lots of data. If you're going to try to build a system to process this kind of data, getting back into cloud mode, it's got a few different steps you need to be considering. Data capture is the furthest upstream, going from source of data through making decisions over here. Capturing is really the first step that needs to happen. You need to figure out what data you want and figure out how to get it into the data processing systems. Some of this could be from sensors, some of this could be from business partners. There's many different sources of data. Once the data come in, the next step is to process it, and I'm going to show you a cloud component from Google called Data Prep for processing data initially. Sometimes it's necessary to mask the data as it's flowing in. If there's some personal information that's revealed, you might want to hide this stuff for privacy policy reasons. You might also want to enrich the data. So if you have some record that you've observed in a streaming context and there's some existing database, it may be useful to do a match, grab the data from the existing database, and append it onto the record for further processing. So that's processing and cleansing. Once that's done, you may want to persist the data. So like I was saying, from these Street View cars, we store data for a long time, not knowing what we want them for in the future, but that we probably want them. So there's generally it's a good idea to be keeping logs somewhere or some representation of these data that are captured in an appropriate format. So now it starts getting interesting. Once you've got all these data collected, you can actually start modeling the data by doing some data analysis through which you can test hypotheses. So maybe you have some idea about how to detect a traffic signal, for example. This is the point at which you would start to use previously existing data to form these kind of questions. So doing simulations, building machine learning models, etc. And then finally, regardless of what type of analysis you're doing, ultimately the data is not useful unless you find some way to take some action from it. And so data use is an important part of this cycle. Usually this is going to be some kind of visualization, a dashboard, a decision support system for an executive somewhere to figure out how to use the data to drive your business. So you can think about the whole process as being an expert support system. And of course, security spans all of this. Operational resiliency and security is critical. If you don't have a system that's running reliably from an operations and security perspective, this whole process is meaningless. So that's really the value the cloud is adding is we do data center operations at large scale for many customers and make sure it stays up and running. Okay, so introducing some specific products. If for those of you who are new to cloud, or if you've been using Google Cloud and haven't seen some of the products, I'm going to talk about these. We'll call out PubSub over here. So this is related to this capture column I'm showing. I'm going to talk to you a little bit about some data processing tools that we have. So there's one called Dataflow and another one called Data Prep, which I mentioned a moment ago. Related to analysis, I'm going to be talking about machine learning engine and TensorFlow. So this is for doing custom machine learning models on the cloud. And then finally, using the data for decision support, you can use something called the Vision API or other machine learning pre-created APIs. This one's for processing images. Or use something called BigQuery, which is general purpose data exploration and reporting. Related to this process and use dimension here, you can really do quite similar things with Dataflow as you can do with BigQuery, or let's say the Vision API. The thing is that what you're getting by moving in this direction within the abstraction is that you get more ease of use by moving this way, and you can deploy a service more quickly. So if you're in prototyping phase, this is a way to really quickly get value because Google has already pre-made some tools for you. But that comes at a cost, and that comes at the cost of not having necessarily the flexibility or the customizability that you want at this end because everything has been pre-made and made some assumptions about what your use case might look like that could possibly be invalid. So moving this direction is sort of making a deeper investment into infrastructure and development of your applications, but it means that it will take longer to get it done. More powerful, slower to develop. So I'm just going to really quickly talk about PubSub. This is kind of an unsung hero of the Google Cloud Platform. It's not especially interesting as its own component, but it can be used as the integrator between all of the other components. So basically, PubSub is the pipe that sits in between component A and component B that lets data move between the two of them. It's a message queue. So it basically looks like this. You have some publishers that are creating data or acquiring data from somewhere. The data is packaged into a message object. The message is published to a topic, so this is something logically related that says all messages going in here are in some way of the same data type for the same purpose. And that has some storage temporarily associated with it, so the topic can be subscribed to by multiple entities, for example. There's a subscription model, and so subscription is basically how somebody who wants to consume the data as a subscriber here shown on the far right can get access to what's in the topic. So rather than having the publisher talk directly to the subscriber, we introduce this additional queuing technology in the middle that allows the publisher and the subscriber to be decoupled and to interact asynchronously. So this is really useful, for example, if you get a big burst of data over here, you don't want to flood your subscriber, and you want to be able to scale these things independently. An example, sticking with cars again, is you might be able to, for example, use PubSub to build a real-time traffic visualization for giving directions on Google Maps based on some data being collected from several Android devices that are telling you, hey, right now I'm at this latitude and this longitude on the map, and I'm moving in this direction. That enables you to build something that looks like this, right, for doing real-time traffic routing. This is an example use case on PubSub. Another type of data, rather than data that are being collected but not analyzed, is data from partners and third parties. So presumably there are other organizations that are also doing similar processes to what I was just showing you, and wouldn't it be nice if you could merge the data because business value can be derived from linking data sets. Okay, so we have a tool for doing this. This is called Data Prep. It's basically thank you. It's an ETL tool for loading data into a data warehouse. And in the interest of time, because there's a bunch of different things I want to show you today, I have a video in my presentation for showing really quickly what Data Prep does, and I can talk a bit more about it after this video. Let's see. I'm going to click this. Well, hopefully this doesn't break anything. So Data Prep takes some existing formatted data, like a CSV file, and lets you access it and pre-process it for feeding to downstream systems. So here you can see we're going to open up some CSV files, blah, blah, blah. It loads them, does an extraction of the data types, and columnarily represents them. So immediately, basically, this drops you into this console where you can look at the data. It has some ability to pre-match against known patterns, known data types, like phone numbers or zip codes and addresses. You can automatically remove rows that contain malformed data or make rules otherwise. And it also has the ability, since JSON is becoming popular these days, to automatically split out your JSON, for example. So we can grab a field, open it up, name the column by the key, put the value in a column,
And then these histograms are distributions of the data being shown. So you can see is there's some interesting shape to the data. Once this is done, we can also, because the data types have been automatically determined, we can join the data as well. So here you can see that some data are being joined by latitude, longitude. So putting these together on the map in the same place. And all of this underneath data prep is a technology called data flow, which that was just being shown here. There's a data processing graph that's created as a result of all of that web-based exploration we were seeing. And because the entire data set's not being processed in the browser, it's only a subset of it. And so the data flow can process arbitrarily large amounts of data. The output can either go back to cloud storage in some CSV format, or frequently what happens is the data are moved into BigQuery, which I'll talk to you about in a moment. That was just being shown on the end of the video there. All right, so let me jump back into my presentation here. Okay, cool. Yeah, so this is showing you, for example, a case where you want to do this might be if you have some transactional data coming from one particular data source, like your merchant processing system, but you had an analytics system coming from, let's say, Google Analytics, and you have the same product key in both of these data sets. Well, by using something like data prep, you can have a regularly scheduled import of these data, and as long as the data formats of these two different data sources don't change, you can automatically do a join of these fields for downstream processing visualization. This thing's really handy. I use it all the time. Because as a data scientist, frequently what we're doing is spending a huge amount of time doing pre-processing and not really doing data modeling, and this automates a lot of that work with data prep. Okay. So I'm now going to talk to you about data flow a bit. So again, thinking about wanting to make decisions quickly, it's important to be able to process data in a streaming context, or at least within very small batches so that decisions can be made quickly. And historically, if you look at these large data processing systems, they were not especially well designed for that use case. So the machines have historically been made for doing batch processing. And so you might be aware of a framework called MapReduce. This is something developed by Google that was then replicated into a project called Apache Hadoop. So that's basically MapReduce, if you know what Hadoop is. It really has only two operations, map and reduce, that you can chain together and process very large data sets. The problem is it's quite difficult to write applications with this framework. Also, because it's batch processing, there's a lot of latency involved in processing the data that are coming in to a MapReduce system. And so that means that you can really only process the data every few hours, let's say, which is all right for some cases, but for anything that needs to be very interactive, it can not match the business requirement. So really what we would like to have is some kind of system that can do processing independent. We can express the process, the data that needs to be applied to the data independently of this kind of batching operation, so that we can make the batch of arbitrary size. It could be, let's say, 1 month long, or it could be 5 seconds long. That's not really, should not be part of the design, that there should be this kind of fixed time requirement if we already know what the steps are that we need to do to apply to the data. So with that in mind, Google had previously developed a system called Milkwheel internally. This was a research publication that we made some years ago. And we've been doing this kind of processing time, streaming data processing for some years now. It specifically started with Google News, which is a very fast web crawler that updates the search results quickly because the news is always moving very fast. And so now we've made this available. Oh, looks like I lost some animation maybe. So the idea is that any given event that occurs, we could basically do a plot that shows these events are happening in order. So blue, blue, yellow, orange, gray, green, red, blue, pink, red, going in time in this direction. But these data, because of the asynchronous nature of the internet, in particular related to mobile phones, which can go off network and on network, might show up in the system at a different time. So these are, we would call these as late arriving data, because even though they occurred here, they don't show up until after the last ends, because the network might have been offline, or the phone could have been offline. And if things were arriving actually at the time they occurred, they would fall on this horizontal line. And so what we have is some skew, where there's basically latency as the points are moving away from this diagonal line. And because they're not all the same distance, the skew in time is actually variable and can cause the points to come out of order. So this is important in an advertising context, for example, where we want to know how to correctly pay out video producers for the ads that were viewed on their system, but we don't have all the data from all the viewers at the point that the payment needs to be made because the phone went offline, for example. So this is necessary for doing tracking payments and tracking statistics. So this system called Beam is able to solve this problem. What we do is we define a data processing window. And so here you can see there's this diagonal line I was showing you earlier. And we can see that events are flowing in at some rate. And based on a tuning of the system, we can define events as being on time or arriving late, and define specific conditions for handling each of these scenarios. So business process may handle on-time data different than late data. So this late event, if it was payment related, should basically be moved into the next system after it arrives so the billing is correctly accounted for. All right. This solves this batch versus streaming problem because you can write one set of code for doing the data processing and implement all the logic and not have to be concerned about whether the system is being processed in batch or real or streaming context. So I'm frequently programming with Beam. I really like it. It's not easy to use, but it's very powerful. It can run on multiple different execution frameworks. It can run on Apache Spark, if you're familiar with this. This is basically the execution engine underneath the definition of the workflow in the Beam programming framework. It can run on Flink. It can run on Apex. I don't really know much about this one. And it can run on Cloud Dataflow. So this is the Google-specific hosted version of Beam. It's a data flow runner, and it runs on Google's cloud. All right, back to scaling. Really, though, I've been talking to you about ingest of data. I've been talking to you about processing of data. But jumping up a level from the concern of a business, really, you don't even ultimately want to have to worry about any of these things. They have business processes that either you build the infrastructure yourself, you use the cloud provider, whatever you did, ultimately you're just trying to get some insights so that you can figure out what direction to take business. Okay, and the tool that we use for doing that is BigQuery, most frequently. This is one of our most commonly used products in cloud, just because it's so generally useful for storing and reporting on data. So what is it? It's a fully managed data warehouse that doesn't have any operational requirement. If you want to use it, you're basically paying for storage and you're paying for number of I/O operations. So how often are you requesting data from storage to do reporting, and you pay per unit of data processed. The data are stored columnarily, so it's a column store similar to HBase or Cassandra, if you're familiar with these open source projects. The nice thing is that when you're looking at records frequently, you don't need access to all of the columns. Frequently columns are highly compressible versus rows. So storing things columnarily is actually higher performance, can save time, and can save money on the query. The implementation of this is not like a traditional relational database because we don't index the data. We just store it as tuples on the disk, again columnarly, which means every query is a scan. That might sound problematic if you've learned about good relational database design that says you should index data and try to reduce I/O. But we need to make sure that the system can scale up to input data sets into the petabyte range. And so it actually turns out to be quite difficult to implement some of these traditional relational database optimization techniques when you're working on a distributed system at that scale, because you basically cannot store petabytes of data on a single machine. So the normal rules or normal techniques that apply break down at that scale. But we did implement it so that you can still use SQL as a query language to get access to the data, and we're actually able to provide very good performance on query across very large data sets by using this kind of technique. How that works, I think I included a couple of slides about this, is rather than storing the data on one hard disk or some small number of hard disks, we store the data with multiple replicas across many thousands of hard disks. And so this means when you issue a query, your data are being pulled in parallel from across our cluster very fast, which means that your database is basically a data center. Google, all of our applications are implemented not to run on a single machine. They're implemented to run on a cluster of machines where our clusters are data centers with many tens or hundreds of thousands of machines. It's basically the world as a computer. We have a scheduling system. This is the basis for an open source project called Kubernetes. I don't really want to talk much about this, but we have a bunch of fancy scheduling technology that can manage many tens of thousands of machines. And we have a very fast network internally, which is how we're able to move the data around so fast. So this is a picture of some of our infrastructure in the backplane of the machines, illustrating the Jupyter network. So Google, we custom built all of our own networking technology in-house. We don't rely on any of the consumer or enterprise vendors we use to buy a router or a switch. We build it all ourselves. The throughput is very fast. It's a lot of bandwidth per data center, and within, basically, from any point to any other point within the network, it's like it's virtually as if you're local. So it's microsecond level latency between any two nodes in the machine. So that means we can do things like have a shared memory pool sitting somewhere in the data center, and do remote addressable memory that doesn't belong to any single machine. You may imagine that's useful if you're trying to do a join, for example. So this is all the infrastructure magic below the level of BigQuery that I was just talking to you about, and we use these very high performance, large systems for all of our applications. Right. It's just another picture of BigQuery. Data coming in either from batch files like CSV files or being ingested in a streaming manner, go to disk, and then are exported at query time to some pool of computing resources that are workers that are processing the data from those disks. That's moving over a very low latency, very high throughput network. And then these computers are organizing in a hierarchical structure to deliver the result of the query out to the consumer who would be over here. So data are flowing in this direction. I can show you a couple of queries just to show you that the performance is pretty good here. And I'm going to show you one that's on a really small data set. I pre-created this. So we have an open datasets project, and stored inside of there is some Wikipedia web access logs. And so I can show you that I can look at the number of page views to Wikipedia in 2015, month of May. And I'll just run that query. You can see it ran in 2.8 seconds, processed 43 gigabytes of data, which is pretty fast. And it's, I don't know, what is that, like 211 billion rows or something like that. So keep that in mind, 43 gigabytes, 2.8 seconds. I can make another query, a pretty similar one, where rather than just looking at a single month of data, I can define a regular expression that will query a series of tables that all have the same schema. And I'm going to query them all at once to do the same kind of request to sum the total number of requests coming across all months in 2015. So that should be something like 50 gigabytes times 12, right? Because it's assuming May was a typical month. So you can see that that ran in 2.1 seconds. Oh, actually that was cached. So let's run that again without the cache. Show options. Don't use the cache. Run the query. Hide the options. Okay, so it is bigger. It's more than 2.8 seconds. It's now running in 6.8 seconds, so it's still not too bad. 460 gigabytes processed. So it's like on the same scale roughly because of that technique I was showing you over here of doing a massive, where would it go? Like a massive scale out across a very large number of hard drives. Okay. Yeah, so that's BigQuery. So to recap, what I've shown you is we've got PubSub for ingesting data, we've got Dataflow for processing data, possibly using data prep, and then we've got a BigQuery as a system for querying or reporting on the data, like if you wanted to get the total number of pages. There's been something pretty interesting that can be talked about now that I've shown you these base components, and I want to talk to you now about some machine learning use cases on top of this infrastructure. So there's a library called TensorFlow. This is an open source project. It's one of the most popular projects on GitHub. I think it's the most popular machine learning project. Google created it and open sourced it. We launched it in 2015. We've been using it internally since before that, and it had some previous names. But yeah, we found it to be very useful, and it's super useful to external developers as well, according to GitHub stats. Just to give you some idea, we're using TensorFlow across virtually all of our projects that are being served up to you as a consumer. For example, TensorFlow is being used to build machine learning recommendations, video recommendations into YouTube. It's also being used for image search. So if you want to use Google to find similar images or automatically label images for you, we're using it here. App recommendations in the Play Store, automatically predicting what word you might want to type on your keyboard in Android. In Translate, it's being used all over the place. This is like one of the most popular libraries used internal to Google within our projects. So popular internally and popular externally. And the thing is, though, is it's sort of difficult to use these machine learning, to build machine learning applications. And I'm going to talk to you a bit about that now. If you didn't want to build your own, if you recall earlier, I was showing you a slide that showed, okay, well, if you want things very customizable, you can build them, and it will take you longer, but you can get a more custom product that's more powerful potentially. And then on the other, that would basically correspond to building something with TensorFlow or using a service called Machine Learning Engine, which is basically managed TensorFlow, just like Dataflow is managed Apache Beam. But if you didn't want to do things in that kind of customized way, and you wanted something pre-trained, you can get going with Google Machine Learning based products immediately. So we've pre-trained some models that you can then just use by API call. So for instance, computer vision, you can upload a photograph and we'll tell you what's in the photograph. Is it a picture of a cat? Is it a picture of a car? Etc. Likewise, we have Speech API. This is equivalent to if you talk to your phone and say, "Okay, Google," or say, or want to talk to Siri on your iOS device, and it will take your speech and transcribe it into text. That's what this API is for. You can upload audio and get text back. Translation is basically text, human readable text to text. And the natural language API, we use this one for actually parsing the text. So once you get some text in some language, we can identify objects within the within that document, for example. So we can know you're referring to Hanoi, Vietnam, or the Eiffel Tower, or what have you. All right. And I'm going to talk to you a bit about some image similarity search examples. So this is built by one of my colleagues on my team. And I'm including it here because it shows an interesting application of using polygon engine and TensorFlow combined with BigQuery to build an application. So the idea here is we want to do a feature vector search. This is going to get maybe a little bit technical for those of you who don't have a machine learning background, but the idea of a feature vector is if you have some kind of object that you want to do some analysis on, frequently how we will represent this in machine learning is the object has a bunch of attributes, like columns, and those columns fully represent the object within the system, and we call that set of columns a vector of features, or a feature vector. So what you can do in order to get to this feature vector is you have some input documents, let's say. You can do some pre-processing on them, say with Dataflow or data prep or some image processing library that leads to a set of feature vectors. Once you have these feature vectors, if you also have some label associated with each of these observations, what you can do is feed them into TensorFlow to build a model that can correctly classify feature vectors to match the, if a new one, if you brought one of them in and asked the model what class it belonged to, it would give you the right class response back because the model is accurately representing the classes of the features that were input. So this is a supervised type of machine learning. Ultimately, then you could store these feature vectors out to BigQuery so that you could retrieve the layer to do something like find similar images. So I'm going to show you how that works. This is a bit of a presentation from my colleague, Kaz Sato. If you ever get the chance to see him speak, he's fantastic. So here he built an application for querying a set of images, 1 million Wikipedia images. He's queried with Elephant. Took 10 seconds to query 8 gigabytes worth of images, 1 million images. And you can see the results are being displayed here. Sorry it's so small. This Elephant image query had a bunch of matches. And he's going to show you now by clicking on some of them what they are. Some of them are elephants and some of them are not. So here's a match that's some geological formation. It was an elephant, but it sort of looked like elephant legs. Here's a picture that matched. It's actually a stone carving of an elephant. So the neural network was able to recognize that as being elephant leg. And here's something that has the texture of an elephant, and it has 4 columns, which are like legs. So it kind of looks like part of an elephant, but it's not an elephant. All right, so we can actually build an application that will, in BigQuery, that will produce this kind of results for doing image similarity search. In practice, what that looks like, what was done is where we imported 1 million images from the Wikimedia project. This is part of Wikipedia Foundation. Put them in cloud storage, and then we pre-processed them with something called a convolutional neural network. So this is one of these machine learning systems built with TensorFlow, and we specifically used the cloud machine learning engine to build this network and execute it, process all these images we had stored in cloud storage. Because that's basically managed TensorFlow at scale, it means we can do the processing more quickly. Once those feature vectors were exported, we put them into BigQuery. And once they're in BigQuery, we can define a function, a similarity function, to find images that are similar to the query image. All right, so let's get deeper into this and see how that works. What was actually exported from TensorFlow were some features, late-state features in this machine learning model. So what happens is the raw image is input here in the convolutional layer 1, and then we do some series of transformations to that image to get to some derived features that are in an abstract space that are different than the original image, but may be easier for the machine to reason about. Some level of abstraction. What that really means, if we looked at what really is inside of those vectors by visualizing it, it looks something like this. The original input layer, so this convolutional layer 1, the input's coming here, our pixel data, which is shown in the bottom. In layer 2, what happens is these pixel data are aggregated into some kind of composite. So you can see there's stripe-like patterns at various rotations. There's also some color gradient patterns and some blob kind of patterns. And each of the different, there's something called an artificial neuron that's in the network here. I'm not going to make this a deep learning talk. But basically there's a matrix here. And each of the cells in this matrix responds to some pattern coming in from the previous layers, connections. And so each neuron is responding to like different gradients here, as I'm showing. And the interesting thing to note, the key here is that the activation of a neuron at a particular layer in the network is based on some composite of things in the earlier layer. So what that means is that we're basically building patterns of raw input. And so as you start combining patterns, you can start to represent very complex things. Here you can see we've got concentric circles, checkerboards and stripes, things that look like insect wings or lines in the sand, etc. Checkerboards. All the way up to representing very highly complex objects like dogs and flowers and bicycle wheels. Okay. So rather than, again, going all the way to something out here, which would represent specific objects, what we're doing is we're capturing and putting into BigQuery some data that looks like this. Some kind of partially aggregated abstracted data that's not any one object, but could be matching in some number of objects and see what objects are similar in that space, that feature vector space. So this is just some code that shows that we're building this graph. This is a standard type of neural network, VGG16, and we want to pull out layer number 8 from this network. Okay? So the point of this is to get out this tensor. We're going to store this tensor into BigQuery. That's done by running the job according to that little snippet of TensorFlow code I was just showing you that we're going to be pulling data in from Google Cloud Storage. We're going to run the job in this region, and then we're going to write the data out to a JSON file, and then this JSON file is going to be imported into BigQuery for analysis. Okay. Once we get these vectors in, we can do something called a cosine similarity. So if you look at the distance or the difference in angles between two vectors, vectors that tend to have small angles between them tend to be more similar, and vectors that have a larger angle between them tend to be more dissimilar. So if we compare the direction of the vectors, we can know which images are similar in the database by looking for other images that have a similar vector direction in the high-dimensional space as defined by this feature vector coming out here, FC8. All right. So to do that, it's basically something like a Euclidean distance search. We're iterating over each of the different vectors in the feature and adding on the square of the difference between them and then square rooting that. So that's Euclidean distance. This is a way that you can define a function called distance for vector 1 and vector 2. So for any arbitrary set of vectors, you can define the distance. And that means we can create a function, create a query where one of these vectors is fixed, where the vector is our query vector. And then vector 2 could be basically scanned across the entire database to find the distances from the input image to all million images in the database. And then we can order these by order by distance, ascending. And so the things which have the smallest distance in that feature vector space will be the most similar images. That's all that's being done. All right, so that's a way you can combine BigQuery with TensorFlow or a machine learning model. I showed you this can scale to extremely large data sets, so it's not limited to only 1 million Wikimedia images. You could do this with the entire web if you wanted to. And I showed you that you can create some custom functions in BigQuery to extend it to handle these feature vectors output by TensorFlow. And showed you that you can use a machine learning model within the context of BigQuery for doing recording. All right, so they use, this has some other applications beyond just image search. You could basically figure out matching between products and databases if you wanted to build a recommendation system. You could organize users who seem to have similar behavior. This might be useful in a financial fraud context, looking at credit card transactions, let's say. Doing music recommendations, app recommendations, etc. So you can see how this sort of technology might be used to build better information processing and organization systems. And that's really what Google's trying to do, is to organize the world's information and make it useful. That's pretty much the end of my presentation. My team wanted me to call out here that we've got a startup credit program. So if you're involved, Google, we love startups. We love innovative stuff happening everywhere. If you're in a startup that is not yet been a recipient of credit from Google, and is either self-funded, basically bootstrapped, or Series A funded, we're willing to give you a bit of money so you can try out the Google Cloud platform. There's a link here, you can go fill out a form. Don't feel that you need to write it down right now. You can contact me and I'll give you the info later as well. But yeah, we have a startup program and we're happy to have you come on board and try out the Google Cloud process. That's the end of my presentation. If you want to try out BigQuery, it's at bigquery.google.com or cloud.google.com for the rest of the cloud services. Again, my name is Alan. Feel free to follow me on Twitter. I tweet about data science and big data and genetic stuff all the time if that's interesting to you. And I'm happy to run out the clock and take some questions or do whatever the organizers want me to do. Thanks for coming to hear me speak. Really appreciate it. So what happens now? I turn off my live stream.
How we can get the presentation?
Probably. I may have to remove a few slides, but most of the information in the presentation I can put up. And usually what I do is I will put slides, I will announce them on my Twitter feed. So that way I don't have to email everybody independently. So look at my account. That's the easiest way to get the information.